I'm interested in random matrices, in particular random orthogonal matrices. I figured I'd start by giving all the necessary background, state some classical results, and then get into some more recent results and maybe hopefully prove some things. So first thing, let's start out and just recall what we mean by an orthogonal matrix, right? So an n by n matrix U over R is orthogonal if U transpose is equal to U transpose U is the n by n identity matrix, right? And then the set of all such matrices, so the set of all bigger, yes, yeah. The set of all n by n orthogonal matrices over R is the orthogonal group. And we denote this with a bold O of n to indicate the dimension. So a couple facts about the orthogonal group that'll come in handy for us. Okay. So the first fact is the columns of a matrix U in the orthogonal group form an orthonormal basis for Rn. Secondly, if we have an orthogonal matrix, it acts as a linear isometry on Rn. Right? So that is, again, if U is in the orthogonal group, then the inner product of UV with UW is just the inner product of V with W for all V, W, and Rn. And lastly, the orthogonal group itself is a compact Lie group. So here, that is, it's a group as well as a compact manifold. Okay, so here's our group of orthogonal matrices. We'd like to know, what does it mean if we take a random element from this group of matrices? Right? And so here's what we would expect. So if U is a uniform random element from our group, and we fix another matrix M in the orthogonal group, then we'd like the following equality in distribution. If we multiply on the left by M, it has the same distribution as multiplying on the right by M, and that has the same distribution as the original matrix itself. Okay? And so what this says, the distribution of our random matrix U is a translation invariant probability measure. So here, invariant measure, say mu. And so if I have, again, a fixed matrix in the orthogonal group, and for any subset of the orthogonal group, mu applied to MA should be mu applied to AM. Should be mu applied to A. Okay. And now there's only one possible measure that does this. So this is a theorem. Right. There is a unique translation invariant probability measure on our orthogonal group, okay. And we call this Haar measure. Okay, yeah.
But when you started the beginning, you said that U is a uniform random element. So even though already to take it, you need Haar measure, right?
So this is what I expect. This is what I want to happen. So I'm saying this is what we'd like a uniform random element to do.
So with respect to some measure, and now you say that this measure is Haar measure.
Exactly. This is what I expect, and in fact, the measure that does it is Haar measure. Yep. So when I'm taking a uniform random element, I'm exactly choosing an orthogonal matrix that's distributed according to Haar measure, right? And so that's what it means when I'm taking a random element from the group, and so I'd like to describe what Haar measure is so we understand that better. And so I'm going to go through two constructions. There's many, right? So let's construct Haar measure. So the first construction I'll use is a column by column approach. Okay. That is, I'm going to start with an empty matrix and fill it in a single column at a time. Okay. The way we do this is you choose your first column, U1, uniformly from the unit sphere. Sn minus 1 contained in Rn. Okay. So the norm of U1 is 1. Okay. Then, to choose the second column, choose U2 uniformly according to surface area measure on the U1 perp intersect the unit sphere. So this is the set of all x in Rn, so that x has norm 1. And if I take the inner product of x with U1, it should be 0. Right. Okay. That gives me my second column. I continue this process of choosing my columns uniformly according to surface area measure from the unit sphere of all vectors orthogonal to each of the previously chosen ones. Right? And so you can see how at the end of this process, if I continue, I'll end up with a matrix U that has these columns. U is orthogonal by construction, so that's good. In order to show I have Haar measure, I just need to see that its distribution is translation invariant. Right? So I need to check that when I multiply by a matrix M in the orthogonal group, I'm not changing anything. Right? So here, again, I'll fix a matrix M in the orthogonal group. Right? Then MU is just M times this matrix that's been constructed. Right? And this has columns MU1 up to MUN. Okay? And the way I can think about MU is the first column, MU1, is then constructed by choosing U1 uniformly from the sphere as before, then multiplying by M. Right. Now, by my second fact over here, M is in the orthogonal group, so it acts as a linear isometry. So it's going to preserve surface area measure. Right? And if I look at the inner product of the second column, MU2, with MU1, again, because it's a linear isometry, it's just the inner product of U2 with U1. Right? And that was 0 from the previous construction. Right? So again, the columns are orthogonal. Right? And you can see if I continued this argument, I would again have a matrix with the same distribution. Right? So I have the translation invariance I needed and then the Haar measure. Right? So one last thing to note here is I only handled multiplication on the left. Right? That's where the compact Lie group comes in, because in a compact Lie group, left translation invariance implies right translation invariance and vice versa. So I just need to check that multiplication on one side worked. Right? So this construction, what I did is I took a orthogonal matrix and then showed its distribution was translation invariant. I'd like to also do a construction where I start with a matrix that I know has a translation invariant distribution and then orthogonalize it instead. So I'll need a definition first. I'm going to define the Frobenius norm. So if I take A and B, n by n matrices over R, then the Hilbert-Schmidt inner product this is given by, take the inner product sub HS, and this is equal to the trace of A B transpose. Okay? And so then the induced norm, so then the norm on A. So the square root of the Hilbert-Schmidt inner product of A with itself. This is the Frobenius norm, or sometimes the Schatten-2 norm. Okay, so let's do that second construction of Haar measure. Okay. This is going to be a Gauss-Gram-Schmidt approach. Okay. So the idea here, again, I take an empty matrix, and this time I'm going to fill it with IID, standard Gaussian random variables. Okay. So I'll fill an n by n matrix X with IID, independent, identically distributed, standard Gaussian. And I'll denote these as a set Xij. Yep. Then it's pretty fast to check that this matrix has a translation invariant distribution. Okay. So we know the density function for this X. Okay. The density X with respect to the product dxij. Okay. This is 1 over 2 pi to the n squared over 2 x minus the Frobenius norm squared on x over 2. Okay. And so now I'll check that if I multiply by a matrix M, so if I take y to be m times x, right, the distribution is unchanged. So here, then the joint density of the entries of y is given by absolute value of the determinant of m inverse over 2 pi to the n squared over 2 x minus the Frobenius norm squared on m inverse y over 2. Okay? Because M is an orthogonal matrix, the determinant of M inverse is just 1. And again, because it acts as a linear isometry, it doesn't change the Hilbert-Schmidt norm when I multiply by M inverse. So this is exactly the same as the density of the entries of Y itself. But I don't yet have Haar measure because this matrix is not orthogonal. Okay? And so I do what we always do when we want to orthogonalize. I use the Gramschmidt algorithm. Okay? And so all I need to check now is that in applying the Gramschmidt algorithm, I'm not losing this translation invariance that I really need. Okay? So the way you can check that is showing that multiplication by an orthogonal matrix commutes with applying the Gramschmidt algorithm. Okay. So here, I'll let the xi denote the columns of x. Okay. First, I'll apply Gramschmidt and then multiply by m. So here, the order will be Gramschmidt, then multiply. So for instance, in the first step, I replace x2, the second column, with x2 minus the inner product x1, x2 times x1. Okay. And then if I multiply afterwards by m, I end up with a second column, mx2 minus the inner product x1, x2, mx1. And similarly in all other steps in the Gramschmidt algorithm. Okay. Now if I do this in the reverse order, so if instead I multiply by m, then apply Gramschmidt, my matrix now has columns m, xi. Okay. So at the same step in the Gramschmidt algorithm, I'm replacing the second column of mx, which is mx2, with mx2 minus the inner product mx1, mx2 times mx1. Okay. But again, because it acts as a linear isometry, I can pull those m's, get rid of those inside the inner product. And so the key was that I ended up with the same exact matrix in the end, and so I haven't lost the translation invariance of the distribution. All right, so this gives us an idea of what we mean by a uniform random orthogonal matrix. We mean something distributed with Harm measure, which we can construct in any of these ways. Okay? All right, good. So the next thing we can ask is, how can we approximate the entries of such a hard distributed orthogonal matrix? So first of all, the asymptotic distribution of the individual entries of such a matrix, this is a classical result. So this is due to Borel in 1906. Okay. So we'll let x equals x1 up to xn be a uniform random point on the sphere. Then the probability that root n times the first coordinate of x is less than or equal to t. This converges as n goes to infinity to 1 over root 2 pi integral minus infinity t e minus x squared over 2 dx. Okay? So that is the root n times the first coordinate of a random point on the sphere converges weakly to a Gaussian random variable as we let n go to infinity. Okay? And so as an immediate corollary to this, if for each n we let un be a random orthogonal matrix, okay, then the sequence of root n times the 1, 1 entry of our random matrices, this converges weakly to the Gaussian distribution. As n goes to infinity. And so this follows from that first construction of Harm measure where we chose the first column uniformly from the unit sphere. So the Borel's result on the sphere gives us the result for the matrix. So we have the individual entries of our random orthogonal matrix are essentially Gaussian. We like to extend this result to higher dimensions. In order to do so, we need a way of quantifying the distance between two probability measures. So the notion of distance I'm going to use is called total variation distance. We let mu and nu be Borel probability measures on some metric space X. Then the total variation distance between mu and nu, which I'll denote as a norm sub TV. This is defined to be 2 times the supremum over all A contained in X, absolute mu A minus nu A. Okay? Where the supremum is taken over all Borel measurable subsets. Okay? So now, using this notion of distance, Diaconis and Freeman greatly strengthened Borel's result about 80 years later. So this is due to Diaconis and Friedman. So again, I'll take X to be a uniform random vector on my normalized sphere root n, Sn minus 1. I'll let n be at least 5 and k be between 1 and n minus 4. Okay. I'll also let z be a Gaussian, standard Gaussian random vector in Rk. Then the total variation distance between the distribution of the first k coordinates of my random point on the sphere x and my Gaussian vector z is less than or equal to 2 times k plus 3, or n minus k minus 3. Okay. So what this gives us is we can approximate simultaneously k entries from our point on the sphere by k IID Gaussian random variables in this notion of total variation distance, so long as k is little o of n. Okay. So in our matrix context, what this says is, again, so long as k is little o of n, then k entries from the same row or column of a random u in the orthogonal group can simultaneously be approximated. And again, this is in total variation distance by Gaussians. And so this led Diaconis to ask the question, all right, how many entries can we really simultaneously approximate? Okay. This is something Diaconis himself, along with Eaton and Lauritzen, provided a partial answer to in the square case, but really Zhang gave the big result on the square case. Right? So what Zhang showed was that a Pn by Qn principal submatrix of a random orthogonal matrix is close in variation distance to a Gaussian matrix when the dimensions Pn and Qn are both little o of root n. Okay? So as I can take a little o of root n by little o of root n submatrix and approximate it simultaneously. Okay? And he showed that this was sharp in the sense that if x and y are greater than 0 and Pn is asymptotically x root n, Qn asymptotically y root n, okay, then the total variation distance does not go to 0. Okay. So in fact, this is the maximal square submatrix that we can do the approximation for. Okay. So putting this result on the square matrix being little o root n by little o of root n together with the original Diaconis-Friedman result of little o of n entries from a single row or column indicates that I can take a submatrix that has dimensions whose product is little o of n, and I should be able to do this always. Okay? So this is the new result. And this is due to myself under my advisor, Elizabeth Meckes. Okay. So here, we'll let Zn be a Pn by Qn upper left block of a random matrix U, uniformly distributed on the orthogonal group, so that is distributed according to Haar measure. Okay. We'll let Xn be a matrix of Pn, Qn, IID standard Gaussians. And then as long as we just know the product of the dimensions is little o of n, if we let n go to infinity, the total variation distance between the joint distribution of the entries of root n, zn, and the joint distribution of the entries of xn is tends to 0. Okay. So this is a nice result in that it recovers the Zhang's result, it recovers the Diaconis-Friedman result, and all of the intermediate cases. Okay. So notice here that if Q over P tends to some eta that is finite, okay, then we're back to Zhang's case. In that case, Pn and Qn must both be little o of root n. Okay? And so there's not a whole lot of new information there. We can essentially recreate his proof. Okay? The interesting case is going to be when Qn over Pn tends to 0. So Pn is going to infinity. It could be almost like n, and Qn is staying bounded. Okay? So here, what you end up needing is you're going to be looking at covariances of traces of powers of Wishart matrices, which I'll do in a second. Okay. And so when you were doing it in Zhang's case, you only needed to go up to powers 1 or 2. And so those are easy to kind of compute by hand. But as soon as you let the powers of these matrices grow with n, they get very difficult to do. Right? So one of the main things that had to be done was figuring out what those covariances looked like. Okay. So I thought maybe this would be the most interesting part to look at, would be the proof of this little lemma here. Okay. So here, the lemma we'll need. Okay. So again, I'm assuming Q over P is tending to 0. Right? And then the covariance of the trace of x transpose x to the h, and the trace x transpose x to the k. This is equal to 2hk p h plus k minus 1q plus pq to the h plus k minus 1 plus an error term delta hk, where this error term is bounded by a constant times p h plus k minus 2 q squared 2 to the k over root h. Okay. So really, the important part for us was we needed these leading terms to cancel with other things. And we needed this bounded part, the error term, to be small enough that when we plugged it into the rest of the work, the total variation distance went to 0 as we needed. Okay. So I thought I would do a little bit of the proof here since it goes into graph theory. Okay. So the idea here, we can take the trace of x transpose x to the h and rewrite it as a sum I1 up to IH between 1 and P, the sum J1 up to JH between 1 and Q of xi1 j1, xi1 j2, so on up to xih jh, xih j1. Okay. So I'm writing the traces as product of these Gaussian random variables. Okay. And now I'll rewrite this as the sum over g of xg, where g is going to be an S graph. So g is an S graph. The way we define an S graph, we plot the ik on a top line and the jk on a bottom line. Then we draw h up edges from jk to ik, and h down edges from ik to jk plus 1. Okay. So that each edge in the S graph corresponds to one of the random variables. And so the product of all the random variables corresponds to an S graph. And so I can count up the number of S graphs instead of counting this. Okay. Let's do a picture to get a feel for this, right? So I can plot the i's. They don't have to be distinct, so maybe I2 overlaps with I4, this. I'll plot the j's on the bottom, maybe J1 and J2 overlap, J3 and J4 overlap. Okay. Then I draw up edges from JK to IK. So here, J4 to I4, and down edges from IK to JK plus 1. So I1 goes to I2, I2 goes to J3, I3 to J4, and I4 to J1. Good? Okay. So now, if I go back to looking at this covariance that I'm interested in, this is equal to the expected value of the product minus the product of the expected values, right? So here, minus the expected value. Expected value trace, x transpose x to the k. Okay. And so I can think of this as being the sum over all S graphs G and K of the expected value of the graph I get by the union minus the expected value of my first graph times the expected value of the second graph. And so what we need to do is we need to figure out how the difference in the expected values can change and count up the number of graphs per class. So we end up with two dominating terms. The first, so recall what the moments of a Gaussian are. So if I have the expected value z to the m, this is m minus 1, skip factorial, if m is even, and 0 otherwise. So the first thing we can do is any of these products where I have a variable appearing to an odd power, those are going to have expected value 0. So I can go ahead and throw away all the graphs with edges of odd multiplicity. Okay? And so my first main term is going to be the case where I have double edges in both of my individual graphs. So the expected value of xg is equal to the expected value of xk is equal to 1. Okay? And then in the union, if I take two graphs that have only double edges and overlap them, I'll have one graph or one edge of multiplicity 4. Okay. So the picture here, maybe my G looks like this with all double edges. Okay. And my K looks like that, also with all double edges. And so the union of the two graphs, I have to choose some edge in both to overlap. And so I get something like this with my G union. Okay. Right. And so this will have expected value 3, right, since I have the one edge of multiplicity 4. Right. And the difference gives me 2. Right. So the last thing I need to do is count up the number of ways I can construct graphs that look like this. So we have 2 H edges to begin with. If I have only double edges, I have H distinct edges. Then I choose which vertices are going to be on top and how many on bottom. Okay. So if I take R 0 up to H minus 1, I can choose R plus 1 bottom vertices. So the J's, and I'll have H minus R top vertices. If I have H distinct edges, I have H plus 1 distinct vertices total. Then we count up the number of isomorphism classes. Right? So here we have two S graphs are isomorphic. If one can be converted to the other, by permuting 1 through P on the top line and 1 through Q on the bottom line. So that is two S graphs are isomorphic if I'm just changing the labelings, really, of the vertices at the top. All right. So the way I count up the number of isomorphism classes, I count up the number of ways I can lay down the edges. And so to do this, I count all the possible ways that you can draw up and down edges when you have two H plus 1 vertices. That looks like H choose R, H minus 1 choose R, and subtract off the ones that don't give you an S graph. Okay. So here, I subtract off the bad ones. This gives me 1 over R plus 1. H choose R, H minus 1 choose R, number of isomorphism classes, and then the number of graphs per class. So this is given by the number of ways I can label those edges. Okay. Or I can think of it as the number of ways I can label the vertices. Right? So I can label the first top vertex with a P, then I have P minus 1 choices for the next top vertex, and so on. P minus H plus R is 1. Same thing on the bottom, I have Q choices for the first bottom vertex up to Q minus R plus 1, minus 1. And so this is less than or equal to P H minus R, Q the R plus 1. Good. And then finally, this constructs one of my graphs. You construct the other graph, so the K graph, in exactly the same way. Only now you must have at least one overlapping vertex, so you have one less new vertex to play with. Okay? And also you need to choose the number of ways in which they can overlap, choosing that edge of multiplicity 4. And I have two HK ways in which they could pick the overlapping, just HK. Ways I can pick the overlap, H from the choice in the first graph and K of choices of edges in the second graph. Good. So putting this all together, I get a term 2HK, sum R is 0 to H minus 1, sum S is 0 to K minus 1, and then all of the things from my first one, and so on. So for the K graph, I get K minus S minus 1, the one next vertex. K choose S, K minus 1, choose S. So that takes care of the first case. Second case, I'll do much more fast, just to explain what the second possibility is. Okay. So the other possibility, and counting up these graphs, would be if we have both of our individual graphs have expected value 0. Okay. So here, xg and xk are both 0. Okay. But when we take the union, it has non-zero expected value. Okay. And so the way this could happen would be is if I had some cycle of single edges or edges of odd multiplicity lying in the one graph that exactly overlaps with the same cycle inside my other graph. Okay. So that when I combine the two, if I lay them over each other exactly, everything has double edges, and then I'm all good. The expected value is no longer 0. Okay? And we can have other stuff going on. That's fine too. Okay. All right, so in this case, you do the same kind of process, counting up all the number of possibilities you can do this. Then you extend to graphs with 6 single edges, and so on and so on and so on, so that you get a couple more of the big sums like this. Okay? And so then the last thing you can finally do with this is this holds always for any P and Q we like, as long as the product is little o of n. Okay? Then under that special condition, Q over P tending to 0, you can start to bound these sums and bound the difference in the expected value in that case. And that's how you end up with that really nice formula I had over there for the covariances. Good? Yeah? All right. So maybe the last thing I wanted to mention is just a result. So the original question asked by Diaconis didn't put any stipulation on having to take a subblock of all the entries together, right? There was no such thing in that original question. And so these proofs all rely heavily on the geometry. But if we allow ourselves to weaken the notion of distance, then you can actually approximate any little O of n entries you like from the random matrix. Okay? So this is just one last result here. So this is due to Chatterjee and Mekis. Okay. So here, if we take A1 up to AK, n by n matrices over R, such that the trace Aij, or Ai Aj transpose is root n delta Ij. Right? We let U be a random orthogonal matrix, and X be the random vector we get by taking trace A1U up to trace AKU. So this is in RK, right? And again, we let Z be a standard Gaussian random vector in RK. Then the L1 Kantorovich distance, which is topologically weaker between my X and my, X and Z, is less than or equal to root 2k divided by n minus 1. Right? And so in particular, if we take the AK to be some set of root n times Eij, where this is the matrix with a 1 in the Ij entry and zeros everywhere else, right? Then this gives us the result that in this weaker notion of distance, we can choose any little O of n entries out of the matrix we like. Right? And so this answers the original question, but in a coordinate-free way. Yeah. All right. Questions?